Hi, everybody. In this lecture, we're going to study Bernoulli equations. Bernoulli equations are a particular kind of nonlinear equations, really a very special form, but that under a change of variables reduces to the case of a linear equation that we learned in last section. So now let's look at how to do that. Okay, so the first thing we want to do is say, what is a Bernoulli type equation? Okay, so Bernoulli equations are anything that can be written in the form y prime plus p of x y is equal to q of x times y to the n. Okay, so when n equals 0, this equation is separable. Because when n equals it's a linear equation. A linear equation of exactly the type we looked at before. Okay, so that is to say that it's you're looking at y prime plus p of x y equals q of x. That's exactly what we did in the last section. And when n equals 1, it's also a linear equation because then it's y prime plus p of x. Now this, when n equals 1, this is a q of x y term, so we can bring it to the other side. So actually, that's a linear equation, but it's actually even simpler than that because in this case, it's separable. Because you can write that as q minus p times y. Think of dy, y prime is dy dx. Leave the x variables, bring them all to the right, the y variables all to the left, and write it down. So you get some, you can work out the answer for that. In particular, let me be a little more specific with that. In this case, let's say, let's let p tilde of x be q of x minus p of x. Okay, and so in that case, we have, so again, I'm doing the case n equals 1. So now I have dy dx is equal to p tilde of x times y. And so I can rewrite that as dy over y is p tilde of x dx. Notice all the x variable things are on the right, all the y on the left, so that's separated, so I can integrate. I get ln absolute value of y is equal to the integral of p tilde of x dx. So as long as we can integrate that, we're good. And now to solve for y, I exponentiate on both sides. So y is e to the ln absolute value of y, which is e to the integral p tilde of x dx. Okay, and you actually get a plus c. When you do this indefinite integral, you get a plus c. But now with the properties of exponentials, that's e to the whatever you get from the integral times e to the c, which is another arbitrary constant. So we can actually get rid of the absolute value signs there. Okay. All right. So that's how you solve it in that case. In n equals 0, it's exactly the linear case that we solved in the last section. So what about other values of n? Can we solve it? Okay. So this is actually a method that goes back to 1696 due to Leibniz, whose name you heard when you studied calculus, hopefully. And basically, again, let me remind you of our equation. It's y prime plus p of x y is equal to q of x times y to the n, okay? And here's the trick. The trick is to make a substitution. You let v be y to the 1 minus n. Okay, so that's a major trick. It is the key to solving these equations. And it's just something you have to learn. When you see a Bernoulli equation, if n is not 1 or 0, then this is the trick. Okay. Why is that a trick that works? Let's see how this does. Well, okay, now we start to differentiate. What happens when we take v prime? Okay, by the chain rule, that will be 1 minus n y prime. I'm sorry, 1 minus n times y to the 1 minus n minus 1. So that is to the minus n power, and then times y prime. So that's just the chain rule. Okay. All right, and now we want to substitute. But before we do that, let's take our equation, which I'll call asterisk, and I'm going to multiply our equation by y to the minus n. Okay, that'll give me the equation y to the minus n y prime plus p of x y to the minus n times y, so that'll be 1 minus n, is going to be equal to q of x times y to the minus n times y to the n. So those two multiplied together give you 1. Okay. And notice that this is, except for the factor of 1 minus n, this is v prime. So this is 1 over 1 minus n v prime plus p of x times, notice this term right here, that's exactly v, and that's equal to q of x. And so in other words, we get that v prime plus 1 minus n p of x v is equal to 1 minus n q of x. Okay. All right. Well, we know how to solve that. Notice that this is a linear equation. For v. So that's what we learned how to solve last time. So it's not quite, this would be what we called our old p. So let's say that's a p hat. And the right-hand side is what we used to call q, but let's call it q hat. So we can use our notation from the last section. Okay, so how did you solve a linear equation like that? You looked for the integrating factor, and we learned that for linear equations, the integrating factor was exactly e to the integral, whatever the coefficient of v was. So that'll be e to the integral p hat of x dx. All right, so let's work that out in this case. This is e to the integral 1 minus n p of x dx. So that is e to the 1 minus n times the integral of p of x dx. Okay, and so we'll multiply the whole this equation by exactly that term. Okay, and then when we do that, so this is the integrating factor that we called mu last time, and when we worked it out, we got that our solution was v of x is 1 over, we call this mu, it's 1 over mu times the integral from some initial point, wherever you give in your initial condition, x0 to x of this integrating factor, this 1 minus n times q of s ds, q of s mu of s ds plus c. Okay. So we're going to see it. We don't want to memorize that. You do not want to memorize this. You just want to remember that you have an integrating factor, you multiply everything by it and work through it. So it's easier to see this going in an example. Okay, so let's do an example. So suppose I give you the problem y prime is equal to ry minus ky squared for r greater than 0 and k greater than 0 constants. Okay, r and k are constants. So you look at this and you recognize, because you have a squared here, that this is going to be a Bernoulli equation, because I can write this in the form y prime minus ry is minus ky squared. So that's Bernoulli. And it's Bernoulli in the case with n equals 2. Okay? So according to our trick, we let v be y to the 1 minus 2, which is y to the minus 1. So then now we start using that trick. So this is the main part of the trick. And now we just start calculating and realize we should get to a linear equation that we can solve. So when I differentiate this, I get minus y to the minus 2 times y prime. So now I multiply the equation by, let me go ahead and multiply it by minus y to the minus 2. I'll put the constant with it. So when I do that, I multiply this equation up at the top, right here, by minus y squared, to minus y to the minus 2, I will get minus y to the minus 2 y prime is, and let me bring the r term to the other side. So we'll use this equation right here. So this will be plus r y to the minus 2 times y is equal to plus k y to the minus 2 times y squared. So notice that reduces to minus y to the minus 2 y prime plus ry to the minus 1 is equal to k. And now we notice that this is exactly v prime, and y to the minus 1 is exactly v. Okay, not v prime, that's v. And so we end up with v prime plus rv is equal to k. So that's a very easy linear equation because r and k are constants. So the integrating factor for this linear equation is just e to the integral r dx, because that's a constant. So this will be e to the rx. And now what did we do with our integrating factors when we had a linear equation? We multiply the whole equation by the integrating factor. Okay. And then you, hopefully on that left-hand side, if you've done everything right, what you have is the perfect derivative of e to the integrating factor times the unknown function, the perfect derivative of that. And double check. What's the derivative of this? It's e to the rx times v prime plus re to the rx times v. So that's exactly right. That's that left-hand side. And on the right-hand side, you have whatever you have. So now we could separate variables. This is d e to the rx v is equal to k e to the rx dx. This is a perfect derivative, so I can integrate on both sides. On the left, I get e to the rx times v. On the right, when I integrate this, I will get k over r e to the rx plus c. And so solving for v, I get v is e to the minus rx times k over r e to the rx plus c, which, rewriting that a little bit, becomes k over r plus c e to the minus rx. Okay, and notice that's what I wrote above, remembering that the integrating factor, the mu, is e to the rx. So this term is 1 over mu. Look back at what we wrote before. Okay. So this is 1 over mu. We integrated. We don't have an initial condition, so we just did the indefinite integral. For us, it was a -1. Q was minus k. And then we had the multiply by the integrating factor, which was e to the rx, and we integrated that. Okay, so that's how we got this term. Okay, and then we just simplified using some algebra. So don't memorize that other formula, just work through it like we did with the linear equations. Except we are not quite done. What we did is we solved for v, but what was our unknown function? The problem in the beginning was given to us in terms of y. So we need to go back and solve for y. So let's see, we have right now that v is k over r plus c e to the minus rx. But v is y to the minus 1. Okay, so let's see, to rewrite that in a more convenient way, I will write that as k plus CRe to the Rx all over R. And now to solve for y, I invert on both sides. So y, or take reciprocals on both sides, is R over k plus CRe to the RK. And that's the solution to your Bernoulli equation. Okay? So with Bernoulli equations, you always do the same substitution, and you just work through it and see what the equation tells you. Okay, before you get to a linear equation, work through our method of linear equations that we learned last time, and then don't forget at the end you have to substitute back to get what the solution y is. Okay, that's all there is to Bernoulli equations. Really pretty simple once you understand linear equations. Okay, bye.